Welcome back to another video of MTX Tutors. In this video we're going to learn everything we need to know about mechanics. In particular, we will see kinematics and forces. Let's start with kinematics. We will see that there are basically three types of motions: constant speed, constant acceleration, and variable acceleration. Let's study these types of motions separately. Constant speed is the easiest of all cases. The speed time graph, because the speed is constant, is just a straight line. And for the kinetic equations, we only have to remember how to calculate the distance. And this is done by multiplying the speed with the time. Now sometimes we might need to change from kilometers per hour to meters per second. And in this case, what we have to do is multiply by 1,000 and then divide by 60 two times to move from hours to seconds. And if we want to do the opposite conversion, so from meters per second to kilometers per hour, we have to divide by 1,000 and then multiply by 60 two times. Now let's see what happens when the acceleration is constant. In this case, the plot is going to look something like this, and we might even have different sections for different accelerations. Now there are quite a few equations to remember. V is equal to u plus a times t. S is equal to ut plus a half a times t squared. S is equal to vt minus a half a times t squared. V squared is equal to u squared plus 2as, and finally s is equal to a half u plus b, and all these times t. These equations, we won't have any other options but to remember them. The last case is variable acceleration, and in this case, when we want to pass from the position, or x, to the speed, what we have to do is differentiate with respect to time. And if we want to go from the speed to the acceleration, we also have to differentiate again with respect to time. But if we want to go from the acceleration to the speed, then we have to integrate with respect to time. And likewise, if we have the speed and we want to know the position, we have to again integrate with respect to t. And in this case, with variable acceleration, the speed time graph is very complex. It can look something like this. In all these three cases, the distance traveled is going to be the area under the graph. So for this, we will have to integrate the velocity with respect to time. And the acceleration will be the gradient of the graph. So for this, we will have to differentiate the speed. And now let's talk about another kind of motion that is actually very similar, and that is vector motion. We will again have three cases. For constant speed, the position vector, we say that it's a vector by underlining it, is going to be equal to the initial position plus the velocity vectors times time. Now for the constant acceleration, we're going to have three equations. V is equal to u plus accelerations times t. R is equal to r0 plus ut plus a half acceleration times time squared. And finally, r is equal to r0 plus vt minus 1/2 at squared. You can notice how similar these equations are to the previous ones. And now when we have variable acceleration, we will do the same as before. If we want to move from the position to the velocity, then we have to differentiate with respect to time. And from velocity to acceleration, we again have to differentiate. But if we want to go from acceleration to velocity, just integrate with respect to time, and the same from velocity to the position. A common example that is a combination of these first two cases is a projectile. In a projectile, for example, we have something like this, and we might be given some position A. We will have the horizontal motion, that this is with acceleration 0, so it is constant speed, and we will have the vertical motion, and in the vertical motion the acceleration will be equal to minus the gravity, and so it is constant acceleration. Now these two equations have something in common. They are connected by the time. And so we might be asked to calculate the speed and direction of motion at A. For this, we will have to first write down all the equations for the horizontal speed and for the vertical speed. And then with these two, we can use Pythagoras to calculate the speed of the projectile, and we can use the inverse tangent to calculate the direction. So this is all we need to know about kinematics. But now let's move on to the most complicated area, and that is forces. So an exercise might say that the situation is in equilibrium, or also at rest, or static. So all this means that the forces are balanced. So what this means is that the speed is constant. And because the forces are balanced, then the left forces are equal to the right forces. And also the up forces are equal to the down forces. We can also get dynamics, and here we are not in equilibrium. So this means that the system is accelerating. So for this, what we have to do is solve F equals ma in the direction of motion, or if we're working with vectors, then use F equals ma, but now with F being equal to R. And what is R? Well, R is going to be the resultant force. So if we have a system with 3 forces, then R will be the sum of the 3. But this applies for systems with any number of forces. So I'm just gonna add 3 dots to say that we just have to add all the necessary forces. And lastly, let's talk about friction. Friction always opposes motion. And so we can have two situations. Static. So static means there is no movement, everything is in equilibrium, and in this case the friction force is always smaller than or equal to mu times r, where r is the normal reaction. And we can also have the limit equilibrium, And this happens when Fr, the friction force, is greater than mu times the reaction force. So we might see frictions, for example, in slopes, and we might be asked if an object is going to move or not. So we might be in a situation like this. Let's say we're given a situation like this one. Let's decompose the situation in all the forces that are acting. So this object will have some mass, and therefore m times g, the weight is pulling down. Because it is in a slope, then we will decompose this into two forces, these two. Now, because this angle is theta, that means that this angle is also theta. Therefore, we have that this force here is going to be, it's adjacent to theta, so it's going to be mg cosine of theta, and this other one is going to be mg sine of theta. Now I'm assuming that the motion of this object is going to be downwards, and so the friction will be upwards. So when we're asked if this object is going to move, then what we have to compare will be this force, the horizontal one, the one that goes downwards, and the friction. So this one is mg sine of theta and the friction. Well, if mg sine of theta is greater than the friction, then the object, this force will win, and so the object will be moving downwards. But if the friction is greater than or equal to mg sine theta, then the object is going to remain at rest. So now let's see some other situations like this one. So in general, if we have a force F that's inclined in a slope of theta, then we will have these two forces. The horizontal one, in this case, it is adjacent to theta, and so it's going to be F times the cosine of theta. And the vertical, it is the opposite of theta, and so it's going to be F times the sine of theta. We may also have situations in which two objects are pulling from each other. And in this case, for example, for the red object, this object will be feeling the tension in that direction. And we could also have the weight, but let's just not consider it here. And this other object is going to be feeling the same tension in the opposite direction. When we have thrust, it is the opposite, so we have again two objects. But now this first object is feeling like it's being pushed in that direction, and the other one feels this force. But sometimes we can have more complicated situations, like for example, two boxes on a lift. So let's say we are given this situation. There is a lift, there is a big box B, and then a smaller box A. Let's say that B has mass big M kilograms, A has mass small m kilograms, and then we have the lift that has L kilograms of mass. Well, we're gonna have to draw a diagram for each of these objects. So let's start with A. A is the small box, and it will be feeling its weight, small m times g, and the reaction from B upwards. Let's call it R. Now B will be feeling its weight, so big M times G. This reaction that B was giving on A, it will feel it, but in an opposite direction, so this will also be R. And then because B is on the floor, it will have a normal force acting in this direction. Finally, let's consider the lift. The lift has the tension here from the cable. It has its own weight, Lg, and it also has a normal reaction here. So when we consider the whole object as one, we will have the weight, the total weight, that's going to be big M plus small m plus L. This is kilograms times the gravity, and then an equal force in the opposite direction. And let's move on to more complicated situations, like when we have connected particles. For example, if we have, let's say, a caravan that is being pulled by a car that is moving in that direction, the car is going to be having a driving speed in this direction. It's also going to feel the tension of the cable, and let's assume that these objects are in the floor. It is also going to have friction, and then the caravan, it will also have friction, and it will have this same tension. Another situation can be like this. So we have two objects connected in a wheel. Let's make the diagram for the first object. It will have its own weight, let's call it m1 times g, and the tension of the cable. Then the second object, it will also have its own weight, m2 times g, and the tension of a cable. And a common error is not realizing that the wheel is also an object itself. So the wheel has the two tensions from both cables, and it also has a reaction, because otherwise it will just fall. And a situation that could be even more complicated is when we have a wheel here, and so we have an object hanging in this side and another one on this side. So again, let's draw all the diagrams. This object is the easiest one. We have the mass times gravity and the tension. This object, we have several things. First of all, the friction. Then we have the weight, m2 times g, the tension. And because it's laying on this plane, then it has a reaction. And we can decompose the weight into two forces, like we did before. So now this angle will be theta, and that means that this force is m2g cosine of theta, and this other force is m2g sine of theta. And last but not least, the wheel. This wheel has the two tensions, and then it has the reaction. So let's zoom in into this section of the graph. Now, because this is a rectangle triangle and this angle is theta, this angle here is 90 minus theta. And so when we divide this by 2, we have 90 minus theta divided by 2 and 90 minus theta divided by 2. So we said that the wheel had the reaction. We have the two tensions, T and T, And so when we decompose these two tensions now onto this plane, then these two forces will cancel out, and we have 2 times this force here. Because this angle is 90 minus theta over 2, each of these forces will be t cosine of 90 minus theta over 2. And so it must be this r, the reaction, has to be 2 times t cosine of 90 minus theta over 2. So with this we finished the video. If you have any questions, make sure to visit our website.